Good afternoon, everybody. We're going to see a presentation from Joop de Huis on side channel analysis on embedded systems. Joop is from RiskCure, a company that does hardware security testing. He's an electrical engineer by training, and he has proudly said a long-time hacker. This is the fourth such event that he has been at here. And he will be answering the question of whether side channel analysis presents a threat for embedded systems. Is it as easy as people think? And at the end of his presentation, he'll be doing a demo, which you might want to stick around for. Please welcome Joop.
Cool. It's a nice tripwire here across, so I won't dare move further. Welcome to my presentation. Like you see in the slide, it's side channel analysis on embedded systems. So I'm actually going to do presume already some knowledge here, which is always a bit tricky. How many people did see Jasper's talk yesterday on side channel analysis? Ah, that's good. Oh, great. Wonderful. At least, yeah, I can assume some knowledge. So that's good. Because actually I won't be talking very much on the details of how to do a correlation or a side channel analysis. I'm much more looking at an embedded system and trying to say, well, if you would want to attack it using these techniques, what are the problems you encounter and what are the techniques that you can use? So first, yeah, who the hell am I? Like the intro said, long-time hacker. I always think, ooh, I'm an old fart if I see this. My current role, before this I did pen testing, that stuff, but now I'm one of the directors of a company called RiskCure, and like you heard, we test a lot of hardware stuff, so we tend to take apart a lot of stuff, and in some cases side channel analysis applies. So side channel analysis is one of the core expertises of our company. So what I'm going to talk about is first setting a scope. Is, okay, what are we going to talk about as an embedded system? And then I'll try to guide you along the things that might make side channel analysis interesting for these devices and why, and also what makes it more difficult or more easy compared to kind of the benchmark, which is a smart card. And yeah, the last part is more of how do I assess a product, and when is it a risk for my product? Because that's in essence the question that everyone asks themselves. Okay, this technique exists out there, but yeah, is it really a problem for me? And when do I need to do something about it? First of all, kind of setting the scope. What kind of devices will we talk about? And I kind of separate two types. One I call microcontrollers, and the other type I call complex processors. Well, of course, it's a very vague term, and there's no clear distinction because it's a range going from one end to the others. But you kind of get the idea behind it. One is a very dedicated processor. It's often a simple 8-bit, 16-bit, and the other is a very complex system. It has multiple cores often, it runs at higher speeds, etc. And we try to separate these two because the application of side channel also divides a little bit along those lines. And if you think, what is he speaking very fast, that's because I've got a lot of slides. I'm trying to keep up the pace. If there's anything unclear, just yeah, raise your hand and I'll try to answer it. So what is a device? Well, of course, embedded device, it has a security function, that's pretty obvious. And the focus will be here on the passive side channels. So what does it mean? It means measuring and not doing the fault injection stuff that Jasper also talked about. But the big question is, of course, why? Well, of course, I already said there's a certain threat, but how big is the threat? And do I need to worry about it? How does it compare to smart cards? A lot of people in our field are very much used to smart cards. They've been testing smart cards for this, these kinds of attacks for 10 years now. So they're very used to this, and it's very difficult for them to compare what they know in that field to the embedded area. And of course, well, what's future developments and some demo stuff at the end. So what is new if you do side channel analysis on embedded systems? First of all, there are two kind of uses for side channel analysis. One is actually getting the keys out, and the other is understanding a system, maybe before you're getting the keys out, reverse engineering. So on embedded systems, you can use it to get keys and PIN codes and unlock codes and feature unlock codes and stuff like that. It all works, it's all been done. And for reverse engineering, you can use it to discover program flow. You can figure out maybe which crypto algorithm is being used, or you can even reverse an unknown proprietary algorithm using these techniques, depending on the leakage, of course. But if you compare this again against the field that's been used so far, actually not much changes. It's the same use, it's just a different device. So when do you start to think about side channel analysis? And this is where there's maybe a difference to smart cards, because with smart cards nowadays, it's a mandated test technique if you're doing a payment card, for instance. Every payment card in the world that's, for instance, under Visa or MasterCard has been tested on this. For embedded systems, of course, it's a completely different world. And that is also because there are some preconditions that apply. For instance, physical access. Is that applicable to your device, and in what sense? How much time, how much access do I have to carry out my attack? What kind of interfacing do I need? With a smart card, it's pretty obvious what the interfacing will be, but with an embedded device, there may be a wide range of varying interfaces that are available, or that you may need to be able to carry out your attack. And then, of course, the cost of equipment, and I already put some stuff on the table here, and you can imagine that cost can go up with a lot of physical testing, so that may also factor in the attack. And of course, again, it becomes interesting when there's a secret inside. You need to gain something. With embedded devices, often unlock codes and feature unlocks are also interesting, so it's not even about the secret key to do your payment, but it's just expanding the possibilities of your device. But also, it tends to only apply when other attacks are much more difficult, and that's kind of a theme that you'll see through this, is that the logical and the physical access protections already need to be pretty tough before you start to think about side channel analysis. So what does a typical setup look like? Well, basically what's in front of you here on the table is exactly this. It's only being replaced by some more portable devices. So we have a workstation, a laptop that does all the processing. It controls an acquisition device. In this case, it's an XY stage and an EM probe. So it's going to pick up the EM field of the chip. And, oh, it's moving. And in the top, there's an oscilloscope. And again, there's a wide range of devices you can use. I think that thing is about 15,000 euros. But on the desk here, I've got one that's 1,500 euros. So, and it still, applies. So also that is something, again, for the cost of attack to factor in. So the question is how can you set up something like this and attack a device? What kind of other activities do you need? And when you do side channel analysis, and you may have seen that yesterday, you need a few prerequisites. Of course, you need access to the side channel. If it's a power measurement or an electromagnetic measurement, or you need to measure the timing of something and you need a trigger line somewhere to measure it from. So you need to have that access. If you don't have it, then the whole attack doesn't work. If you're doing a so-called differential attack, a crypto attack, you do need to have input or output data of the crypto to be able to do your attack with. So you take your measurements, but you still need to get that data. If it's all embedded into a system and a protocol that's difficult to penetrate, then already that represents an effort to overcome. Then you need to minimize the noise. And again, for smart cards, there's been devices designed to minimize that very much. However, in an embedded system, you're dealing with the power supply that's being given to you by the embedded device. And, well, we'll see what you can do or have to do to overcome that. You need to know what to measure. If you know the hardware crypto operation maybe takes a microsecond, and you have an embedded device and it goes in over Ethernet or a serial cable, when does it happen, that single microsecond that you want to measure? So you need a trigger signal. And can you derive it from the design, or do you need to implement something yourself to be able to do that? And then you need to link the data to the operation that you measured. So you need to know this measurement was this data going in. And if you've got a stream of data going in and you have crypto going on, it may be quite difficult to match up the measurements and the crypto and the data, and your whole attack won't work if that doesn't match up. It's a statistical attack, so it's very sensitive to that. So you see there's a lot of prerequisites that you need to take into account before you do an attack. And then we switch back to smart cards. The reason being, like I said, 10 years of testing on smart cards sets a benchmark, a body of knowledge of how you do this on these cards and how you set them up. And of course, it's difficult to convey all that knowledge now and directly into the room, but I'll use a few tables to compare some of these things to an embedded system to explain a little bit of the difficulties. The tables are quite big, so they'll be posted on the web. I won't go over every entry, but it's kind of a brain dump of things that we come across. If you look at a smart card, you see the contact pads. It's all been ISO standardized. So that makes the testing also much more convenient, because you know what the power line is, you know what the input line is. You can send data in and trigger and do your whole acquisition process fully automated because of this kind of standardized interface. And that's one of the big changes when you go to an embedded system. So if you think about a smart card processor, in general, we talk about a microcontroller. It's a CPU. They're getting bigger, but still, for instance, the crypto core is still like 20% of the die, and it's still a tiny, tiny engine compared to all the CPUs we use around ourselves today. So if you start comparing to a smart card what a maybe more complex embedded system would look like, you already see that there's a lot of things to take into account. For instance, a lot of the complex CPUs these days have multiple processors inside. So how do you know which one is doing your stuff, and how do you isolate that one from all the others doing other stuff, which is all noise compared to the smart card that's just doing what you tell it to do, namely generating a certificate or something like that. The engine itself, the crypto engine, on a complex CPU is just a building block, and they can scatter 10 or 20 AES cores over the chip, whereas the smart card has only one, and it's D1. So you get more like the needle in a haystack kind of feeling when you look at a complex CPU compared to a standard smart card. However, there are also other parts, and that is, for instance, that a lot of crypto in embedded systems is in software, or partly supported by software. Also, there are no countermeasures. We hardly encounter any countermeasures in embedded systems compared to smart cards. So there are pros and cons if you look at this picture, but if you have a high-end CPU, I think the cons outweigh a little bit the pros. If you look at acquisition, so like I said, if you have a standardized ISO interface, you can do your measurements and measure your power. What about an embedded system? Well, everyone now knows the PCBs, and you have seen the sites, and maybe you built them yourself. How do you measure the power line if it's a multi-layer PCB and the components are very close? So you get the challenge of just getting access to the channel is already part of the attack, which weighs in, whereas the smart card you just insert in your reader and you're done. However, there are also advantages. A smart card interface is relatively slow. You cannot change the behavior of the interface, whereas the embedded system, it may be modular, and you may be able to replace some parts without endangering the crypto part, but it may help your attack. So you can customize the embedded system more for your attack than in the case of a smart card, where you just have to deal with what's given to you. Also the power. We see embedded systems taking, in the set-top box world, taking a few amps, and in the gaming it's even worse. It's like 10th of amps. How do you measure that compared to the milliamp voltages of a smart card? So again, it's not a black and white picture. You see things that are much more difficult, and there are things that are actually much more attractive. One of the attractive things in embedded system is if you can customize it, it often can run much faster than a smart card. And for a DPA attack, you need measurements, and to encounter or overcome noise, you need a lot of measurements. So now I can do, we have done on some chips 5 million measurements or more in a day, whereas for a smart card that's maybe a week or more. So you have some things that actually work in your advantage. So when you start thinking about testing, what do you encounter? First, a small remark about testing and attacking. We are a security testing company, and that means that we don't have to go through the full attack like a real attacker would have to go. That means that if you have an embedded system and half the time that's spent on reverse engineering how it works, we generally don't have to do that. We can focus on an engine that we want to know the leakage of and concentrate all our work on that. If we then have a finding, then we can just translate this to the world outside and factor in how much time people would have to spend to reach that stage to see if it is a problem for the product, yes or no. So most of our work is focused at creating the optimal testing environment as opposed to having the most realistic attack. But still, that means that we have to overcome and understand, of course, a lot of these aspects that everyone has to overcome. What do you need to do? Well, first of all, you need to control the crypto. Like I said, you need access to the data. You need to be able to trigger on it. So you need to be able to know when it happens, and preferably actually cause the crypto to operate. In the ideal world, I pass the data in and it happens, and then I measure at the right time. So reaching that stage already needs preparation. Then I need, of course, to link the data with the measurements. I need to, okay. I thought the tent was collapsing, but it's not so bad. The efficiency of the acquisition is something you may want to look at to optimize that, to improve your attack. And like I said, you need to balance the increased efficiency and the increased complexity. A few examples. So timing analysis. If we look at timing analysis, actually an embedded system is often more interesting than a smart card. With a smart card, you're bound to the official interface, and if in the official interface there's no timing variance, then that's almost all you can do. In an embedded system, you have a lot of peripherals on the board that all happen and signal things at a certain time. And you only need to have a few that actually correlate to the timing that you're interested in to get a real attack. So other things are runtime issues with CPUs, with cache timing. If you Google cache timing attacks, you'll see quite a few things. And that all applies to software systems in embedded systems too. One thing that with timing that you can do with power measurements and EM measurements is increase the accuracy. Like I said, if you have a smart card and you can just see input and output, if I measure the power signal of that same chip when it's happening, I might see timing variation in the power signal. And then still it's a timing attack, but I use the power signal to do it. A very well-known timing attack is actually this, that if you do something in software, and especially if you don't really control or understand the API, you may have a problem. And one that occurred, I think now 2 years or 3 years ago, is a timing attack on the Xbox. So what you see here is an Xbox with a small helper board called an Infectus board, which is an FPGA. And it's used to carry out a timing attack on the signature checking of the bootloader. So the way it worked is that the Xbox is protected by a secure boot chain, and it calculates HMAC, SHA-1. An HMAC is a hash of the whole firmware with a secret key. And in the end, you get 16 bytes that say, okay, this is a real one. And you need to compare it to the one that you stored. And this is where the software comes in. The software naive implementation did a byte-by-byte comparison and stopped if there was a first wrong byte. So you get a timing dependency. That if there 5 bytes wrong is a different time than if there are 10 bytes wrong. And this timing could be measured in a very specific way. What they did is they put the Invectus board on the system. It could modify the NAND flash real time, and then it would observe a diagnostic port. So these were 8 bits, they were exported off the chip, they were just on the PCB, you soldered the wires to it, and it would give an error code every time the hash was wrong. And by just timing how much time there is between the reset on the CPU and when that code appeared on the bus, they could time the difference in the comparison. And then it just, the small board just brute forces that with help of a PC, and it takes about 2 hours to find 16 bytes. And that's the way the Xbox was broken, and they could run Linux on it. So this is to show that these are actually real attacks. The thing is that this only occurs after the Xbox chips have been protected to such a level that you don't get any easier access in another way. And it's fixed, of course. Power analysis. So what you see here is a board of a BlackBerry. And the idea is, okay, this is a CPU, it has a secret key. How do I do a power measurement on this CPU? And if you look really carefully, you don't even see traces on that PCB. It's just one flat layer on top, because all the layers are used in the middle of the board. So to be able to actually access the power line, you either have to go all the way off the board and just measure the external power, but then you're measuring power for everything on the chip, which is really noisy. Or you have to make some kind of interception somewhere in the middle of this PCB design, which is quite a challenge even for an electrical engineer with some soldering skills in BGAs, etc. So a power attack might seem attractive. There are no countermeasures, but it still can be quite a bit of work. And sorry? No, because that's not a power measurement. What you measure then is just the input voltage.
Yes, but you have current flowing from one side to another side. So you have resistance in the PCB, and you measure the differential between two capacitors.
Well, that's often not the way it's implemented. If you look at the design of how, so the idea is if there are a lot of decoupling capacitors often on the board, that you can use them to do your measurement. Actually, the point is that most of the time you want to get rid of all the capacitors because they flatten out your power profile. So it's more the opposite. You want to find one place to cut the wire, do your power measurement, or inject your own power, and remove all the decaps that are present to get as much spikes in the power signal as you can get, because the spikes are the ones carrying the information. The last point, basically you always need considerably more knowledge on the target compared to a smart card. EM analysis. First, maybe an explanation of what electromagnetic analysis is. Here in the next slide, I have a picture of a probe tip, and that's the probe that's mounted here. And in the tip, you see a very, very tiny coil. In the probe itself, the metal housing is an amplifier. So what it does is it picks up the local EM field around that coil. And that's a technique you can use to have kind of non-invasive measurements. So we don't have to open the PCB. We just float this thing above the chip. And I'll show you in a minute a little bit of how that works. What it does, it adds something called the dimension of space. Instead of a power line, which is one dimension, you now have an XY where you can put your probe and you will measure different things at different places. This is especially interesting, again, from a smart card perspective, where you have countermeasures on the power line. They have a lot of capacitors and you try to flatten it, but you don't have control in your design, or not much control in your IC design, on how the field will look like above the chip. So this is what that tries to exploit, is to figure out if EM can then be better. The big question is, of course, where do you need to be with your probe? And there's no clear rule yet to know where the place is. So I'll try to show you a little bit what comes out of that if you put it above a board here. What we see is that EM generally tends to add if it's a small area you're interested in on a relatively big chip, a big die. So if it's a microcontroller, then most of the time the power contains all the information and is a better signal. And of course, if it's non-invasive. So maybe time for a quick demo. So what have I got here? I understand it's a bit far away, so I have kind of zoomed in. Actually, what you have is an XY, motorized XY stage. It can move. Beneath it is a small board with a processor, and it will be running an RSA. It's a very simple implementation of RSA, also not a very long key size, but it's just for the principle to show you that you actually do see different signals when you do these measurements above a chip. So for that, I have to switch. Oops, this does not look good. I need to plug this in. It's always with demos, of course. That sounds good. Okay, the whole screen looks a bit warped, but that's because of the sizing. So what we can do here is we can, and this is part of the software that we have to do this analysis. So there's commercial solutions. There's also open source software on the internet to do such an analysis. What I can do here is I can operate the motorized stage. Oh, I need to select the correct COM port. It's using a serial cable to the development board, to the CPU, to feed it with data for the RSA. I also have a short video. You'll see that there's also a trigger line, which is on an LED. So we're using a GPIO line to trigger at the time of the RSA. And with this, I set the positions. Oh, wrong way. So now you probably don't hear anything, so I can try and play the movie at the same time. Let's see if this works. Okay, this doesn't work. So what I now do is I move the tip to the opposite corner. Oh, wrong zone. And that defines the square area where the scan needs to take place. So I need to define these two areas. And then when it's set, it will do a measurement, send an RSA for each position, do the measurement, and then make a plot out of it to show the relative strength. And I'll set it to 15 by 15. And then I'll go on with the talk, and at the end, hopefully there's a nice picture. And now it's moving back. Oops. Of course, more demo effects. For some reason, it doesn't see anything on my... Yeah. Finally, no. They always tell me make movies, don't do demos. Now I know why. Another bug. Okay, I'm going to quit the demo here. I already arranged that I can do more demos in the afternoon in a tent. I'll explain later where it is. Is this visible? Yep. So basically what happens is this. So you see it will move around the thing on the edge. Turns around. The tip of the probe is floating just above the silicon package. What we found is that it isn't necessary to open up and decap the package. So the millimeter or so distance between the real die surface and the probe doesn't influence the signal strength that much anymore that it's necessary to do this. What you see here is the trigger signal. So this is a small wire connected to the LED pin that supplies the trigger for the oscilloscope. And then on the screen, yeah. So this is the plot that you get. So what you see there is the blue and the red and the yellow. And what is calculated is the spectral intensity of the signal. So this is doing an FFT and creating a single value of the intensity of the signal. And by using a few sliders, you can choose the frequency bands to get a picture above the chip. And actually, what it looks like is this. So this is what you already saw. And here are the sliders I told you about. What you can see is that there are clearly areas that are more active than other areas. What happens if I slide is that actually it jumps around quite a bit. And now you see actually a square area that seems to pop up or actually pop down in this case. Anyone an idea what that is? Sorry? I cannot fully hear it, but the die, yeah, okay. Yeah, yeah, so you see bond wires and you see where the die is placed, because the die itself actually doesn't emit that much EM. Now it distorts because the rest is so strong, it seems like there's no signal over the die, but there is signal over the die. The question is, what is the interesting signal? So bond wires may convert or transport interesting information like keys or stuff like that, but then you can also sniff them on the chip pins. For a real secure processor, actually everything that's interesting happens on the die. So you need to set your limits of your scan to only that area in the middle, and then it will show you where the areas are that are active. And actually, I think by setting certain limits, you'll see that there are, well, fakely there's an area here that's active. If I click on these areas, you can also see in the trace, now remove this, that the patterns are also really changing. In this chip, which is pretty simple chip still, you see that there's a basic pattern everywhere, but if you've got more complex CPUs, you'll see that the basic pattern is actually changing quite a bit, and there's only a few areas where you see a clear pattern. I saw a finger going up. Okay, the frequency for measuring depends on two things. The length of the operation you want to measure, and can you fit it in at the frequency you're measuring at, so what's your buffer size. But generally you want to be quite a bit over the frequencies that you're interested in. So the Lacroix that we use is 10 gigasamples, and we use the full 10 gigasamples for anything like at 300 megahertz. So we tend to try to go as fast as we can. But for RSA, for instance, this is RSA, it's a very slow process in software. So actually this is measured at 25 megahertz while the CPU is running at 57. So, and you can go much lower and still get the bits up. We use about 10 times the cutoff frequency of your low pass. And the low pass determines, yeah, for instance, just above the core frequency of the chip. And then our rule of thumb is about 10 times faster if we can. Yeah, but in the end, the things we are interested in are mostly hardware crypto cores, and they are very fast. So we have very few situations where we want to measure really long. And also, if you then have to do processing, you don't want to have too much data. So most of the work in SideChannel is compressing the data. How can I keep the interesting stuff and get rid of as much of the noisy stuff? So resampling techniques and filtering techniques are important to try and reduce the data. Okay, I saw a sign that I need to hurry up, so let's try and do that. Yeah, some practical encounters. So we were looking at the Xbox and thinking, well, maybe power measurements. This is the power entry of the Xbox CPU. It's a complete flap of copper on the PCB. I think several tenths of amperes are going in over 3 lines, so there's not even a single point in the PCB that you can intersect and measure the power on. So actually power measurement is quite a challenge. And then if you want to use EM, the chip is beneath that power, beneath that heatsink. And if you take it off, the chip dies. So actually it seems all nice, but in practical situation, you can still encounter quite a few difficulties. Another one is, this is a Beagle board with an OMAP chip. The new packaging techniques shown above. You have the CPU underneath, and then a memory chip with 2 dies on top of the package, and it's all soldered together. So now, if you put your EM probe above, it sees the memory chip instead of the CPU. And here you see the power distribution chip, which is tightly coupled with the CPU. So you need to somehow figure out where to measure your power. So actually, again, in practice, you will encounter quite a few more difficulties. Okay, so this is about all the difficulties and all the pros and cons. Wrapping up, what does it mean for a product? Basically, side-channel analysis actually does break security. There are very few countermeasures, especially microcontrollers leak enormously. That's why 10 years ago, all the smart cards were broken with side-channel, without exception. Also, all the cards of 5 years ago, we break today, and that's a progression of the technology. So for embedded, you can trust that you can break crypto with it. However, like I've shown, you need a certain level of control that might not be so easy. There's a high noise level in the more complex CPUs that you need to overcome, and that increases the effort. And the question is it sufficient to overcome it, or do you need to add more countermeasures? What are countermeasures? Basically, we distinguish 2 types: hardware countermeasures, software. Hardware are all kinds of die design techniques, specific circuitry to make power consumption equal, stuff like that. In software, you can do all kinds of randomizations, you can change your algorithm, you can change your protocol to kind of improve your design against these techniques. If you have a key that's only used for 1,000 times and then it changes the key using a sequence algorithm, then you only get 1,000 measurements with 1 key, and then your side-channel attack that works at 50,000 doesn't work anymore. So there are all kinds of ideas in the design that you can use to improve a product without actually changing the hardware yet. When talking about countermeasures, and this is especially for people building things and designing things, it's good to know that there's a company out there called Cryptographic Research, founded by Paul Kocher, who kind of invented this whole class of techniques. And they have a wide range of patents, and they license the countermeasures, especially to all the chip manufacturers currently. But if you need countermeasures, you always need to consider that licensing may apply, depending on what component you use, etc. But also for knowledge on countermeasures, they are the ones that come up with all those new protocol ideas to strengthen your design. And they're in San Francisco, by the way. So, and then kind of taking everything now together, I try to make this table to kind of see how I would rate the difficulty of an attack on a certain kind of system. And this is by no means the truth or the Holy Grail. I put a special note there that it still happens that on a very complex CPU with a very bad RSA, we break it within a week. But still, for a rough idea, it gives you a feeling for the effort that you require. And that goes, of course, from a basic microcontroller, which is in fact more like a smart card, but without countermeasures, it's fairly trivial. So a 1-2 week effort, and that's including figuring out the whole attack, is sufficient. That means that afterwards you can do the attack in a few hours most of the time, because when you know what to do, it's just measuring and doing the attack. And then you see that adding countermeasures and also moving to the more complex CPUs, it adds in the complexity of your tools that you need to use to do the analysis, and it adds in the setup time that you need to actually get the side channel going. So what do we see in the developments? Increasing high-speed acquisition, so like the oscilloscopes, they keep in, the CPUs go up, but the oscilloscopes go just as fast. It becomes more mainstream. There are a few sites. There's OpenSCA on SourceForge, which is a set of MATLAB scripts by an academic, Oswald, that distributed this on the internet. There's the DPAcontest.org, which is a contest to crack a set of files that they put up there and see who gets it the fastest. So there's a lot of interest now in the more mainstream world, as it were. Processor-based, what we see is much more features and countermeasures in chips. So not so much countermeasures against side channel, but a lot of features in secure storage, secure boot, things that make it like removal of JTAG, fusing of JTAG, password protection of JTAG. So you don't get that easy access anymore, and it's not just about reversing the firmware and then you get the keys. Okay, then, well, let's hope this is going to work. Final demo, and this is an SPA attack on RSA. And sorry? Yeah, I was just going to explain. This is a picture to explain this. SPA is simple power analysis. So that means that you only need one measurement or a few to actually do the attack. And you don't need a statistical attack on multiple measurements. And what you see here, it's a measurement of an RSA operation on a contactless smart card. And the way it works is that you can implement RSA in various ways. And the simple way is to do a square operation for a 0-bit and a square multiply operation for a 1-bit. And that already tells you if I can distinguish a square and a multiply, I can break RSA. So if you use the naive bitwise implementation of RSA, you'll get something like this. And in this case, it's the width. So you see that there's a slight timing variation between this square and this multiply, and this square and this square and the multiply, and that means that you can read off the bits. So a similar kind of demo is now set up here. And again, if it works, what I'll do first is I'll move the probe to a better position. And the idea is that when we measure, you get something like this. So it looks kind of raw. I have to move the probe a bit. Oh, wrong way. Oh, wrong way. So I'm not completely sure because the XY scan didn't work if this is the correct position, but I'm just going to try, see what comes out. So what we're going to do is just take about 10 measurements, this time at 250 megasample, so that's like about 5 times faster than the CPU frequency. But actually for RSA, that's not so relevant. And then we just run it. And actually, I think we can also hear it. Do you hear something here? Okay, so it is a little bit to show that with a fairly simple setup, so this is just a loop antenna, and I think it was also shown yesterday, with a hand scanner, AM demodulation, it's already picking up actually part of that RSA. It's a short RSA, so it's over quite quickly, but the information in the signal is also audible already with AM demodulation. And RSA is quite slow, so probably you can also make a decoder if there's this time variation in the chip. So what the measurement looks like is this. I'll turn this up again. And you don't see that much actually. And maybe if I zoom in, you start to see something, and probably you can already now figure out what's going on. But I can also optimize the signal a bit by just using some filter techniques. I can build a chain, and what I do is I do some steps. I make an absolute of it. That's because it's an EM signal, and the EM is differential, so I make it absolute. I add a resample to compress the data a little bit, and in this case I'm going to choose a quarter of the CPU frequency. And then I add a low-pass filter to pick out the lower frequency components, which is the RSA bit calculation, which is actually quite slow. I think 10. Let's just try this. See what comes out. Oh, actually, it already looks a bit better. So now you already start to see some variation. And actually, it's a bit difficult to see, but this is actually the first square and a multiply, and a square and a multiply, and a square and a multiply, and a square and a square and a square and a square and multiply. So actually here we're already again seeing the 1, 1, 1, 0, 0, 0, 1 bits of the RSA in there. And this is not very atypical of any RSA in software. So we typically break even on like 300 megahertz complex CPUs if there's an RSA in software, or even only with a hardware multiplier. This is broken in maybe 10 traces, and often only in one. Okay, this was what the target actually was. So the idea is that this could be a more or less secure platform. It has locking of JTAG, it has internal flash and RAM, so you could make some software around this that kind of locks it down, and it has the RSA key in there as a secure thing, but then this is kind of the signal you get from it. Bringing me to the conclusion. Well, they are different. There are obstacles, and there are things that are easier. That's basically the lowdown on it. What we see is for basic microcontrollers, it's definitely a threat. And for the complex processors, it's more like, okay, depends how much you're protecting. What can you do? In the end, if you want really strong protection, you do need strong countermeasures. That's basically the message. Ask for them. If you're building something, ask your manufacturer, did you think about this? We get manufacturers only when customers ask for it, and no, never otherwise. Also, do not only think hardware is secure, because it leaks. And finally, if you really want to know what's happening, you need to measure. That's also, we sometimes are also amazed at how difficult or how easy it might be to do something like this. It's a physical process. It's not by design, so it's very difficult to say in advance something on a target. That's basically my presentation.
Do we have anybody with questions, comments, remarks? There's 1, 2, 3.
So you use a probe for magnetic field. What about grinding the chip, for example? I thought about grinding chips and then to probe the field that is stored in the flash cells, and so you can read the key that is flashed somewhere.
Like physical invasive probing of the chip?
Yes, you have to grind it, and then you have to probe the field that is stored in the capacitor of the field effect transistor.
Yeah, well, in the end, there are a lot of things possible.
Have you tried it?
Sorry?
Have you tried it?
No.
Okay. What about getting secret keys from smart cards? What is the best approach to do this?
What's the best approach? Well, there's no best approach. Power and EM measurements is what we use, but laser, let's say laser attacks are the... Well, I think maybe this is better for afterwards. Actually, a guy in the yellow T-shirt here on the first row is a guy building a laser station now. So if you want to know anything about that, ask him. And I'll be over the hill. On your left, there's a big white tent on the camping ground, and I'll be there with this setup later. So if anyone wants to see it, then.
Hi, thank you for your talk. If I understood correctly, you have your coil in the plane of the chip.
Yeah.
So you actually measure the EM component perpendicular to the chip.
Yeah.
Have you considered flipping the coil 90 degrees so you can get a better signal?
Yeah.
And you can also get direction information of the signal.
Actually, we are still also investigating that. We did investigate that and came up with the horizontal positioning. But we also see now new probes that also use vertical. So it's still, what do you want to see? And it's very indeterminate. We do see things this way, and in the vertical plane you also see things. And it's difficult to say which is better, or when do you see more, or what technology beneath it is important.
Okay.
Hi. So as I understood, in the SBA attack, we compare the bit 0 and the bit 1 by seeing if that's a square or square and multiply.
Yes.
So if all the time either it is 0 or 1, I always square and multiply, but for the 0, I don't store it. So what's the attack then?
It could be a solution. Your RSA will be longer in time, and you have to make sure that it's exactly the same time. We have had a situation where there was only 1 clock difference on a 3 megahertz CPU, and we could see the 1 clock difference between the real and the false multiply. I'm not sure when I need to switch, so...
If a CPU makes use of spectrum clocking, does that actually defeat your measurement method?
Sorry, I didn't fully get
the
it.
CPU uses spectrum clocking, so it actually modulates the clock by using frequency modulation or some method pattern. Does it actually defeat your measurement method because maybe you're using very small frequency band?
Yeah, varying clock is difficult, and it's also something that they now use in smart cards. It's free running clocks, and also more spectrum as a countermeasure of syncing up your measurements, because that's the problem. Every time you need to have the measurement of the crypto at the same position in time or in your measurement to do the attack. Okay?
Do we have any more questions? No? Please go and watch his demos. Job, thank you very, very much.
You're welcome.